Hello and welcome. Today I'm going to be talking about large language models and the future of NLP. My name is Connor. You can find me at NP Collapse on Twitter and other symptoms of the inevitable decay of our society. I am an AI researcher at German startup Aleph Alpha by day and loose hacker collective at Luther AI by night. For those who haven't heard of Luther AI, we're a loose research collective, aka a glorified Discord server, interested in scaling, alignment, and open sourcing ML research. We are most well known for our ongoing project to build an open source GPT-3-like model, but it's not the only thing we're doing. You should drop by sometime. So today, I want to tell you a story of three GPTs and why I think these are really important. So by now, I think everyone in the grandma has heard of GPT, especially GPT-3. But I think a lot of the most interesting parts of the story can kind of get lost in the in some conversations about these models, where it's sometimes hard to tell hype from bullshit artistry. So I want to tell what I think is the really fascinating part about GPT-3 and the whole story behind it, and why I think it's pointing towards a whole new paradigm of how machine learning is going to be done in the future. So just to start off with some of the basics, so we're all on the same page here. The GPT family of models are autoregressive language models. So what does that mean? Well, it means that they work on text. They're language models. So you put text in, you get text out, kind of. And what they're trained on is huge dumps of the internet, all the kind of stuff like forums and Wikipedia articles and chat rooms and whatever. And their goal is to predict the next word given the context they've seen so far. So maybe they would see a sentence like pears are, and then maybe it would autocomplete with green or delicious or whatever else makes sense to the model in that context, given what it's learned from the huge amount of text that it has seen during its training. You interact with these models usually by providing a prompt. There are other ways to interact with these models, but this is kind of the most flashy one that people know from GPT-3. So in the previous example where I said, pairs are, that was the prompt. I gave a piece of input text that the model should then work with and then complete on. That's what's called a prompt. And there's another important word here called parameters. And you can kind of imagine these GPT models, they're neural networks, a specific kind of neural network called a transformer. All those details don't really matter for this discussion. But basically, you can imagine them as these huge piles of numbers. And each of these numbers is called a parameter. And you can kind of imagine each number as like a knob that you can twiddle to make the model do better on certain tasks. So you can imagine that the knowledge or the skills or whatever these models are capable of is in a sense encoded inside of these parameters. So the reason these parameters are interesting is because the main difference between the GPT models is not any new algorithmic insight or some clever architecture change or something, but more just a huge increase in compute and size of the models in between the generations. So the GPT-2 model, the largest model, was about 1.5 billion parameters in size, and at the time that was already outrageous. That was unimaginable that was this huge. I remember when the BERT paper first came out, another famous model, kind of similar to GPT models, came out. The paper almost apologized that the outrageous size it had of 300 million parameters. I don't even know when the last time was I used the 300 million parameter model for anything other than debugging. How times change, huh? And so the GPT-3 model then was a whopping 175 billion parameters. That's really huge for our current state of hardware. So just to give you a feeling of just how big that is, usually you would want to keep all the parameters of your models in GPU memory for best performance. And to keep all those 175 billion parameters in memory, and even at just half precision, you're talking on the order of 350 gigabytes of GPU, not CPU, GPU memory that you would need to load this model. So there's no way you can fit that on a single GPU. So you have to have many GPUs that are all interconnected, and which all makes the whole thing much more complicated, of course, to train and to build, and so on. But really what's despite all these engineering challenges, and there are engineering challenges to building models this size, the fascinating thing is how they're just the same thing, just bigger. Of course, more data and stuff, and but ultimately, GPT-3 is just a 100-fold scaled up version of GPT-2. And despite that, the difference in using these models is qualitatively extremely different. Like if you just use GPT-2 versus GPT-3, it just feels so different. So as an example, a good friend of mine is currently working on a GPT-powered video game called Project Electric Sheep. Check it out. And when back in the day when we first started working on it a little bit, we used GPT-2. This was before GPT-3 came out. And so the premise of the game is that you enter like a keyword or a phrase or something, and then the game generates a dream world with like characters and themes for you to explore, generated by AI. So one of the things that we wanted the AI to do is to generate names for the characters in these dreams that would be thematically fitting to the keywords. And so like if you enter the keyword Hollywood, you might want to generate, some actor names or something. And if you entered something about Lord of the Rings, you would want to generate Lord of the Rings themed names and the like. And with GPT-2, this was really hard. You had to really try to get the right prompt and give it like examples and have it like follow lists and that didn't even work reliably. But with GPT-3, you just could kind of just ask it. You just said, this is a video game about a dream, about this theme. Here's a list of character names. And it just worked. Like this was really quite shocking at the time. Sure, it doesn't work every time. Sometimes you'll output something stupid, or sometimes you'll go off topic, or sometimes you'll get confused or something. But really the remarkable thing is that it worked at all. I think this is something that the anti-hype about these models tends to overemphasize, is how these models fail. And yes, they fail a lot. But it's kind of remarkable that something so freeform works at all, ever. So what I really think is one of the big stories behind these models, what's really so crazy about these models, is what are called scaling laws. We discovered these things, these scaling laws, is that as we scaled these things up, as we gave them more compute and we gave them more data, they just kind of kept improving without really doing much more than that. So to explain this concept, I sometimes show this meme here. We have traditional learning. You have to keep careful over fitting and statistical properties and do feature engineering, whatever. Well, with these, large models, just stack more layers, lol. Just buy more GPUs, man. How hard can it be? And of course, this is a bit of a joke, but also kind of not. So from the GPT-3 paper, we got beautiful graphs like these. So what we're seeing here is on the y-axis, we have the performance of the models. Lower is better. And on the x-axis, we have different parameters that could be varied to make the models larger. So in the first graph, we see the amount of compute, so the amount of GPU hours that we put into these models. And we can see this as these models. So each line is a different model of a different size. The further we go to the right, the larger the models are. And we can see as we train these larger and larger models with more and more compute, they seem to really follow this line quite closely. And we see a similar thing in data set size of parameters. As we scale up the data set, as we scale up the number of parameters, it's quite remarkable how they just follow these empirical power laws pretty closely. And just keeps getting better. And GPT-3 was definitely not the limit to this. And this all kind of then resulted in this, I think, really rather astounding graph here, where what we see here is on the x-axis, again, is the amount of compute that we put into our models. And we see that as the amount of compute goes up, the ideal allocation of that compute, so whether to train on more data or to train on the same data multiple times or such, or just make the model larger, becomes very dominated by the model size. So what this means is that as you get more and more compute, it's more efficient to make your model larger than it is to get more data or to train on the data multiple times in many cases. Of course, larger models do need more data, but it grows much slower than the model size itself does if you do this optimal allocation of compute, which is kind of crazy. Like, I remember being taught, when I learned machine learning, that you should only always use the smallest network possible to avoid overfitting and stuff like that. I was still taught that back in the day, and that seems to just be wrong. I mean, not for all cases, not in all situations, obviously not, but at least in like this specific application area of large language models, that seems to just not be true. Just if you have enough compute, just build the biggest model you can. Of course, you also do need a large amount of data, but it's not that much data. It's a lot, but it's a tractable amount of data compared to the model size that you'll be training it. So that's already kind of crazy if you think about that. That already throws out like a lot of the stuff that we would traditionally associate with classical machine learning and statistical learning and stuff. And then we also get this weird new paradigm of prompt programming, which is really quite strange compared to other ways we've had to interact with these models. In the past, when you trained like a model, some statistical model or even neural network model, usually you trained it with like a very specific task at hand. Sure, there are some RL models that can play games or whatever, but let's be honest, those were never relevant in like practical applications. Mostly you had like a very clear, like, it labels 1,000 different dog breeds or whatever. But with this prompt programming, which is kind of this idea of finding the best prompt, you can get your model to often do like a lot of tasks that it was never specifically trained on. So like with GPT-3, you can get it to, write blog posts in a specific style, or write, a specific kind of novel or poetry or whatever. Or you can get it to summarize a text, or even to translate into other languages. It's not state of the art for probably any of these other than writing. Like, it's not very good at summarization. Its translation is definitely not state of the art compared to, a focused model that is only optimized for translation. But it's kind of remarkable to me that this works at all, ever. That we never told the model to learn, to translate English into French or something. But then just by asking the model to do it, it somehow picked that up just from unsupervised learning on a, huge pile of text. I find this quite remarkable. And, if this wasn't even crazy enough, it's like this prompt programming really matters. And one of the wildest things I found when, studying these models is how just telling GPT-3 to be better often works. So friends of mine wrote a paper about this where they showed as an example that in the original GPT-3 paper, the way they evaluated translation skill is they used a prompt which had the form of English, English sentence, French, and then the model would autocomplete a French sentence, hopefully. And my friends found you could get like a statistically significantly better performance, like several percentage points, a non-trivial increase, by instead using a prompt that looked kind of like the English sentence is translated by the masterful French translator as autocomplete. And the masterful was really important. If you left that out, the performance degraded, which is wild if you think about it. It's like the way I think it works is that basically the model learned to emulate lots of different kinds of users and people on the internet. And by default, it will emulate a median internet user, which is probably not great at French. But if you tell it, oh, you're a super intelligent, excellent French translator, then in a sense, it will try to emulate the best French translator it knows, which is kind of crazy. Like, that is not how anything we used to do in AI really felt, at least to me. If the way we interact with these models, the way they're trained, it's qualitatively, I feel, so different from the kind of machine learning I got taught at school and stuff. And of course, to bring this back to scaling laws, as model size increases, the prompting also becomes easier and more performant. This is this effect that I talked about earlier with my friend in his video game, is that with GPT-2, it really, it was hard to get the model to actually do what he wanted to do. It was kind of stupid. It would get like off topic and such. It would get confused. But GPT-3 just kind of gets it. Like, not all the time, not for everything, of course not. Like, there's a lot of things these models do totally hilariously wrong. But again, it's remarkable that it works at all, ever. And with GPT-3, like everyone I know who's used like both models extensively says that like GPT-3 just kind of gets it. It's just like it needs less hand holding. You just kind of tell it something, and you even like misspell a word or something, but it still kind of gets what you want it to do, which is kind of crazy. It's like we have this graph here from the original GPT-3 paper, where what we're seeing here is what's called few shot prompting, where you give the model several examples of what you want it to do, so it knows better what to do. So, for example, let's say you wanted the model to solve a math problem. You might give it a few examples of solved math problems so it knows what you're going for. And you can see with the green line here, which is the GPT-2 size model, it doesn't really know what you want. It doesn't really learn much from what you want by giving examples. But if you look at the blue line, which is the largest size GPT-3 model, by just giving it a prompt, just telling it what you want, the performance increases dramatically. And this is I think this is related to this concept of GPT-3 just gets it. Is that in a way it's easy, it's capable of understanding what the user wants and then outputting that behavior way more consistently than these smaller models do, which is, again, something that I find remarkable and not something I would have necessarily predicted. Oh, if you decrease the loss by 0.4, suddenly the prompts go up, from, like 5% to 50% performance. Like, what the hell? This is kind of wild. So what does this mean for the future? So I think these models are going to be extremely important for the future. I think these are really, in a sense, general purpose models that will be used in many, many applications in the future. So Stanford recently released a paper where they talked about how they've coined the term foundational models for this. And whether you think that's a good term or not, I think that's debatable. I think it kind of points into the direction of how these kinds of general purpose models, they know a lot of things. I'm not trying to make like a philosophical point here about minds or anything. I'm just trying to point out that GPT-3 in some sense knows quite a lot of useful things about text and also about the world. It knows a lot of facts from Wikipedia, and it knows a lot of things about grammar, and those are like useful subroutines, so to speak. There is, like, in a way, you could kind of think of GPT-3 as this general purpose library of lots of useful things that you might want to do when solving NLP-ish type tasks. And you can then build on top of this to make, a cool chatbot or a summarization thing or, a writing assistant or whatever, just, through further fine tuning or, good prompting or something like that. I think that's going to be more and more common in the future, that you have these really big models that are really expensive to train, but then have a lot of useful things that you can build on top of to build something really useful. Unfortunately, I think this also means that training these models will become increasingly expensive and inaccessible. I don't like this. I don't endorse this, but I think this is just an unfortunate reality of how these things work. If scaling these things up more and more, just makes them better and better, then whoever has the biggest computer, whoever is willing to spend the most money, is going to get the best model. This is just an unfortunate fact of how these things work. And of course, making things 10% more efficient is a worthwhile thing to do. And a lot of people do work on stuff like that. But ultimately, even if you make, training a small model 10% more efficient, that just means that the big guy can train a 10% larger model. So again, it'll be a moving goalpost. I think in a sense, we're entering an era of high energy ML. And what I mean by that is that us computer scientists have kind of been spoiled for a long time. And we're kind of used that, anybody in their bedroom with a laptop can do cutting edge computer science work in many, many cases. And that's not been the case for most sciences and, for a very long time. If you're a particle physicist or an astrophysicist or a geneticist or something, you need access to very large and very expensive hardware to actually be able to do, cutting edge experimental work. And I think that more and more we're going to move similar towards high energy physics. We're going to move towards high energy ML. Is that to do the really cutting edge work on these super, super high powered models, you're going to need access to super, super high powered computers that are super, super expensive. And that's kind of unfortunate. I do hope that, academia and governments might pick up the slack there, but we'll have to see. It seems likely to me that a business model that's only now starting to emerge is that large corporations will kind of rent out large models as the base for other products. We're seeing the prototypical version of this with OpenAI's API, in that they don't give you the model to sell. They build this very large model. It was very expensive to train, had like a large fixed cost, and now they're kind of renting it out to other people to build products on top of. I think we're going to see more of this, where like large companies like Amazon and Microsoft and Google and whatever will build these really powerful and general purpose models, not just on text, but also say like images or videos or whatever. And then other companies will use these as kind of infrastructure, the same way now that we rent like cloud hardware or operating systems or buy operating systems from these big vendors. We'll do a similar thing where we take these large models and then fine tune or like, build a small head on top to get the model to do what we want. This is obviously unfortunate for many reasons. Okay, misspoke there, just cut this part out. This is obviously unfortunate for many reasons. These large companies, of course, are not necessarily perfectly aligned with her interest. And this is a large part of why Luther AI exists. So at Luther AI, what we're interested in doing is we're building large models in the open for free for hopefully making them accessible to everyone. There's no money involved. We all do this in our spare time for free because we think it's important. We believe these kinds of models will be important for the short, medium, and maybe even long-term future. We really think that these large models will be a really fundamental part of the future tech stack, basically, that will build that future powerful, useful AI technology will be built on these kinds of things. And so I've written a pretty long, I've written an essay about this, which you can read if you're interested in a bit of more of a philosophical treatise about why I think what we're doing is important. But basically, on the one hand, of course, it's important to help more people utilize and benefit from this powerful new technology. It would be a massive shame and a massive waste, if this super powerful new technology was only accessible to a small hand of Western mega corporations. I would find that very very unfortunate for several reasons. And I do hope that academia will pick up some slack, but they haven't really done so yet. It's the same way that academia and governments fund large physics projects and similar. I hope that they will do the same with funding large AI projects. It's actually quite funny. The other day, I was talking to someone who works with the Summit supercomputer, which is one of the largest in the world, and just so happens to have a great architecture for doing AI work. And they commented about how it's kind of interesting how Summit doesn't really have any big AI projects, like compared to the large, climate models and cosmological models and such that are going on there. And those are all great work, and I'm really glad they're getting done. But it does seem kind of a waste that, some of the, most important work of our time, which I think includes AI, is, kind of just not present in our supercomputing centers. I think that's going to change in the near-term future. I think academia is starting to wake up and notice how important these things are. So I hope that will improve in the future. But ultimately, what I think is a much bigger problem is that corporations have incentives to downplay the weaknesses and the risks of these technologies. These are very expensive to train. It's a big investment, and they want to make a return on their investment. That's just how business works. And that's why I think it's really important that there are people like I would ideally love just having a big community, vibrant community of hackers, understand these models, that research these models, that take them apart, that break them, that see how they can go wrong, how they can be misused, how we can improve on them, so that we can trust these technologies more. Because ultimately, we can't stop AI, and I don't think we should either. AI is coming. And we have to do our best to understand and control it. Because if we do, I really think that AI could be one of the best things to happen to humanity maybe ever. It can solve innumerable problems that we are facing and improve the lives of billions. But it is a double-edged sword, like any powerful technology. And it's going to come down to whether we can learn to wield it. Thank you. I hope you enjoyed. If you did, why not drop by Luther AI sometime? We're a pretty fun group of people, and I'd love to see you there. Thank you.